Hello, everybody. Happy Earth Day. It is April 22nd, and we are going to talk about 3 classes of organic compounds known as the ethers, the aldehydes, and the ketones. And I've got some key players sitting here on the table with me that we will talk about. So let's begin with the ethers. Please take out table R, and I've got it blown up here at the bottom. Organic compound group ether. We've got the functional group. It's an oxygen in the middle. I call it the oxygen sandwich. And there's going to be some group of carbon backbone atoms attached to that oxygen. And we have our example. It's methyl ethyl ether, which we'll get to shortly. Ethers have a variety of uses, and some of them are anesthetics, and some are used as solvents to make perfumes. Now, from table R, I have this example. This is the condensed formula, and I've noted what I call an oxygen sandwich. So when you look at the condensed formula, if you just see that oxygen in the middle of 2 carbon groups, you know you have an ether. Let's write this out as a structural formula. CH3, oxygen sandwich, CH2, and CH3 again. When we name this, it is called methyl, ethyl, ether. So, major hint, you're going to see the name ether in the formula name as well. Methyl group, ethyl group, and this is an ether. And I have a ball and stick model of methyl ethyl ether here. If you look carefully, here is our oxygen in the middle of the 2 carbon groups. All right, let's look at another example of an ether. I've partially drawn the structural formula for it. Again, you can see here, you have the oxygen between 2 carbon chains. We always assume that these are all hydrogens if they're not written in here. So in naming this one, we've got an ethyl group. We've got another ethyl group. And because we have 2 of the same R groups on the outside, we're going to call it diethyl ether. Not too bad. Let's try our 3rd example of an ether. We can be given the name methyl propyl ether. It's pretty hard to say. When we are given the name, we're going to think about what the carbon chain length would be. If it's methyl, it's 1 carbon, CH3. There's going to be an oxygen in the middle, that oxygen sandwich. And then we've got a propyl group. There are 3 carbons in a propyl group. Methyl, propyl, ether. Okay, so let's move on to aldehydes. And if we look at the blown up example from table R, okay, aldehydes are going to have a functional group, C double bonded to an O with a hydrogen. So it's really, there's some kind of R group, some amount of carbons attached to a C double bond O and a hydrogen on the other side. And our example is propanal, Al, in the ending. Think aldehyde, propanone. Just so you know, there's a variety of uses for aldehydes, and some of the more common uses are, in fact, the most famous aldehyde, I would argue, is formaldehyde. It is a biological preservative. And then other aldehydes are used for a variety of perfumes and cosmetics. Okay, so we're going to look at the example propanone from table R, and let's just kind of dissect it here. We've got 1, 2, 3 carbons involved in this aldehyde. We know it's going to be propan. Key part there to the naming of aldehydes is that they will always end in Al. Notice this group, this carbon double bonded to oxygen, this is actually known as a carbonyl group. Okay, an important feature. It's a functional group. So we have the carbon chain. One of those carbons is part of a carbonyl group, double bonded to oxygen, and always one end of an aldehyde is only going to have a plain old hydrogen there. That's important. We're going to note that in a few examples ahead. Here is the most famous aldehyde that I would argue. This is formaldehyde. Using the IUPAC naming system, though, we would call this methanal. Okay, it's a 1-carbon aldehyde, so we use the prefix meth, methanal. We have our carbonyl group. We definitely have one end that is only a hydrogen, but it happens to be, and this is the simplest of aldehydes, it happens to be that the other end is only a hydrogen as well in this case. But all aldehydes have a carbonyl group and only a hydrogen on one end and some other R group. Here is propanone. Okay, here's our carbonyl group, carbon double bonded to oxygen. And here's 3 carbons, propanone. Oh, and I actually made methanol as well. Isn't that cute? Let's look at those together. Methanol, 1 carbon, propanol, a 3 carbon. They both have that double bonded carbon to oxygen, carbonyl group. Okay, we are now going to move on to ketones. Looking at table R, we've got the functional group. It is also a carbonyl group. But notice, by the way, in a ketone, there's just 2 dashes. There's not just a hydrogen here. Ketones have 2 different groups that will be bonded on either side of this carbonyl group. Whereas aldehydes, one of those will always only be a hydrogen. So this is really important to be aware of. So they're similar, but I would say aldehydes are simpler, right? Because one side is always only a hydrogen. There are many uses for ketones, but some common uses are nail polish remover. Acetone is a ketone. And then paint thinners are also ketones. Our ketone example, right from table R, is 2-pentanone. Let's see why it is called that. Let's count our carbons. 1, 2, 3, 4, 5 carbon backbone. Pentanone, ketone, pentanone. 2, what is the 2? That 2 is indicating 1, 2. The second carbon has that double bonded oxygen. And by the way, this is that same carbonyl group that the aldehydes have. But notice, there's a carbon chain and another carbon chain here. So that makes this a ketone. Just to write that out, here's our CH3. Here is our C double bonded to O. Here is CH2, CH2, CH3. And this is 2-pentanone. Let's look at another example of a ketone. In this case, we have a 3-carbon backbone. Propanone. That's the name. That's it. Now you may be thinking to yourself, why is it not 2-propanone? Because I'm going to tell you, it's not 2-propanone. There's no need to indicate where that double bonded oxygen is in this ketone. This is the smallest of all ketones. And this, by the way, is acetone. It's nail polish remover. But this smallest ketone, there's only one location for that double bonded O. It has to be the middle carbon. Because if that double bonded O was on one of the end carbons, guess what you would have? You would have an aldehyde. I will show you that shortly. Before I get to that, here's my propanone ball and stick model. So we have our carbonyl group, double bonded oxygen to carbon, and we have 2 R groups on either side. Total number of carbons is 3, and therefore it is propanone. Let's look at propanal, the aldehyde, and propanone, the ketone. Aldehydes and ketones are similar in that they both have a very similar functional group, the carbonyl group, carbon double bonded to oxygen. But if you look carefully, all aldehydes will have a hydrogen on one end. Could be here or here, but it'll only be a hydrogen on one end. The other end is going to have some kind of R group. In this case, we've got 3 carbons in that R group. So that becomes propanal. But when we look at this ketone, which is also a 3-carbon backbone, one end is the R prime group. The other end is the R group. Now, these 2 ends in this particular case are the same. They are 1-carbon chains on each side. But you could have a 1-carbon chain here and a 2-carbon chain there. They could be different from each other. Bottom line is, when we look carefully at the molecular formula for both of these, C3H6O, C3H6O. They have the same molecular formula, but they have different structural formulas. Do you recall what that's called? Excellent. Structural isomers. So propanal and propanone happen to be isomers of each other. And just a quick look at those ball and stick models again here. We're always in the aldehyde having only a hydrogen coming off from that carbonyl on one end, whereas a ketone will have 2 different carbon groups coming off of that carbonyl group. That concludes our lesson for today. I hope you enjoyed it. Bye.